Yeah.
Today we are going to study isentropic efficiencies. On isentropic efficiency means it shows how close your system compared to an ideal system. So you're going to calculate how much energy transfer by work is required for an actual system, and we will do again for an ideal system, and you will do comparison, the how much difference is going to be. For example, if we want to evaluate an isentropic efficiency of a turbine produces power, W dot out. So you can calculate this power assuming that this is an ideal turbine which is reversible, and you can calculate this energy transfer by you can calculate this power by the actual turbine. So if you calculate how much power is produced by an actual turbine, W dot A, and divide by how much power is expected to be produced by an isentropic turbine, which is an ideal turbine, I'm going to say W dot S. Of course, an isentropic turbine is going to produce more power than the actual turbine. So this isentropic efficiency has a value between 0 and 1. 1 means the actual turbine can produce power as much as an isentropic turbine. That means the turbine is an isentropic turbine. In reality, actual turbines have a lot of ED possibilities. Therefore, isentropic efficiency is going to be less than 1. But if you have two different turbines, one has higher isentropic efficiency than the other, then you can say the one with higher isentropic efficiency has less irreversibilities, so it is more efficient turbine than the other. Okay. What about the compressors or pumps? Compressors consumes power, so you can also calculate isentropic efficiency by using the power consumed by actual turbine and the power consumed by an isentropic, it's a compressor. You can calculate the power consumed by a compressor or pump, and you can also calculate the power consumed by an isentropic turbine and isentropic compressor. And if you compare these two powers, you can say isentropic compressor may consume less power because it is more efficient system. So the power consumption by actual turbine is greater than the power consumption by an isentropic turbine. So in this case, if you want to determine the isentropic efficiency, the power consumed by actual turbine goes to denominator, and the power consumed by an isentropic turbine goes to the numerator. In that way, this efficiency has a value between 0 and 1. So a simple rule is that whenever you have a thermodynamic system, you can calculate how much power it can consume or it can produce. And you will calculate two different powers, one by the actual system and the other by an isentropic system, and whichever greater goes to denominator and whichever less value goes to numerator, so that the efficiency, this isentropic efficiency, can be between 0 and 1. And we know, if the isentropic efficiency is getting close to 1, that means that it is more efficient system. And the ideal system is going to be when the isentropic efficiency is 1. So when you design a thermodynamic system, the goal is going to be in trying to maximize this isentropic efficiency. In other words, trying to minimize the number of irreversibilities so we can save energy. Okay? So the concept of this isentropic efficiency is pretty simple. However, we need to, if you want to understand, how we calculate that, the best way is to look at an example together. Okay? So we are going to solve this problem. We have an adiabatic turbine, and we have the information at the inlet and the exit, and we know how much power it can produce, which is 6 megawatt. Then we are going to calculate the isentropic efficiency of the turbine, which means we need to calculate the power output of not the actual turbine, but an isentropic turbine that has the same inlet condition and the exit condition. So that's what we are going to do. Okay? So let's solve this problem. The simplest way to solve this problem is, you are going to do, the two analyses. One is for an actual turbine. So actual turbine. And the other one is going to be the isentropic turbine. Of course, this is the ideal turbine. And isentropic means entropy S remains constant. In other words, the difference in entropy is going to be 0. Then let's analyze this actual turbine first. The turbine looks like this. It has one inlet, number 1, one exit, number 2. It produces power, W dot out, and that is 6 megawatt, 6,000 kilowatt. At the inlet, we have 8 megapascal, 600 degrees Celsius, and 80 meters per second. So 8 megapascal, 600 degrees Celsius, and 80 meters per second. So we have the velocity, the average velocity of this stream. If the average velocity at the exit is different from the inlet, then we may need to consider the change in kinetic energy. Anyway, at the exit, we have a 70 kilopascal, 160 degrees Celsius, and 140 meters per second. So we see there is an increase of velocity. That means we need to consider kinetic energy change. The first question is, we want to determine the mass flow rate. So we want to determine m dot. So let's do that. We can use energy balance equation. But this time we see there's a velocity change. So we cannot use, the general, the simple, the turbine energy balance equation that we studied. So in this case, you can start with the general energy balance equation for steady state open system. Q dot in plus W dot in plus m dot at the inlet, which is number 1. This one has specific enthalpy H, specific kinetic energy, velocity square over 2, and specific potential energy, gravity times elevation z. It's going to be q dot out plus w dot out plus m dot at the exit, number 2. This one has a specific enthalpy, kinetic energy, and potential energy. First of all, it says on adiabatic system. What is an adiabatic system? Adiabatic system means there's no heat transfer. So we can neglect Q dot in. And the turbine produces power, does not consume power. So it doesn't consume power. So there's no W dot in, but it produces power. So there is a W dot out. And there's only one inlet, one exit. M dot number 1 is the same as M dot number 2. So I'm going to remove these subscripts to show that there is only one m dot. And we can neglect potential energy change, but we need to consider kinetic energy change because there is a significant velocity increase. So we are going to consider the rate of enthalpy and the kinetic energy at the inlet and the rate of enthalpy and the kinetic energy at the exit. So the energy balance equation is going to be m dot h1 plus v1 square over 2 is going to be w dot out plus m dot h2 v2 square over 2. So this is the energy balance equation that we can use for this turbine system. Okay? Then let's see what we know. This one is how much? 6,000 kilowatt. We know the inlet velocity, 80 meter per second. We know the exit velocity, 140 meter per second. We do not know the specific enthalpy values at the inlet and at the exit. So if you can determine H1 and H2, we can find m dot, the unknown. Okay? So let's do that. We know the pressure and temperature at the inlet and at the exit. Can we find H1? Yes, that's a simple table problem that we did in the first exam, right? So let's do that. We have a 8 megapascal, 600 degrees Celsius. The numbers are pretty high, so I guess it's going to be superheat vapor, but let's verify that. So I'm going to use 8 megapascal to make a property diagram. So at 8 megapascal, we can make T, TV, TH, TU. I'm going to say TH because we are interested in H. So TH diagram looks like this. And we need to know 3 reference properties. They are T-set, HF, and HG. By the way, you don't have to find all the values. Since we know the temperature 600 degrees Celsius, if you know the saturation temperature, then we can determine where is our system. So what is the saturation temperature at 8 megapascal? At 80 bar, which is 8 megapascal, he said is only 295. He said is only 295. Then what is the temperature at the inlet? 600. So where is the 600? Up here. So what is the phase change process? Number 5, superheat vapor. So this is 600. We have phase change process number 5, superheat vapor. And if you know you have a superheat vapor, then how can you find their properties? You go to table A4, superheat vapor table, find 8 megapascal, 600 degrees Celsius. What is the property that you are looking for? H. So H is going to be 3,642. So from this, H at the inlet is going to be 3,642 kilojoule per Kelvin. I'm sorry, kilogram. Okay. Then I can substitute this number into this energy balance equation. H1, that is 3,642 kilojoule per kilogram. What about at the exit? We have a 70 kilopascal, 160 degrees Celsius. We do not know the phase change process, so let's determine the value one more time. We can make another pH diagram. Temperature, specific enthalpy diagram. At what pressure? 70 kilopascal. Either way, you don't actually need to make a property table at this pressure because we know the saturation temperature at 100 kilopascal. What is the saturation temperature at 100 kilopascal? 100 kilopascal means that the pressure in this classroom, what is the boiling temperature? 100 degrees Celsius. So if the pressure is even less than 100 kilopascal, the saturation temperature should be less than 100. Then what is the temperature? 160. It's pretty high. So you know it's going to be superheat vapor, but let's modify that. This pH diagram looks like this. We need T set, HF, and HG. Then what is T set at 70 kilopascal? At 70 kilopascal, T set is only 89.95. 89.95. So what is the temperature of our system? 160. That's pretty high. The 160 is up here. So what is the phase change process? Number 5, superheat vapor. This one. Number 5, superheat vapor. Then what is the specific enthalpy of superheat vapor at 70 kilopascal, 160 degrees Celsius? H is going to be 2798.2. So from here, H2 is going to be 2798.2 kilojoule per kilogram. Now, this one goes to here, H2. So that is 2798.2. So we have everything but m dot. Can you determine m dot? Now, yes. So what is the mass flow rate? Oh, I don't have it. 7.17. 7.17 kilogram per second. That is the mass flow rate. There's one thing you need to be careful in this energy balance equation. What is the unit for this H1? Kilojoule per kilogram. What is the unit for this kinetic energy? We have a meter per second square. So it's a meter square per second square. So what is the unit of meter square per second square in joule per kilogram? That's going to be joule per kilogram, not kilojoule per kilogram. Okay? So this H1 has a unit kilojoule per kilogram. So there's a kilo. But from chapter 1, we studied dimensional homogeneity. and meter square per second square is going to be joule per kilogram, not kilojoule per kilogram. So make sure that you divide by 1000 from this value to make sure that you use kilojoule per kilogram. Okay. The same goes here. I didn't say 6 megawatt. I wrote 6,000 kilowatt. So you don't need to worry about any unit conversion in the equation. Any question about the first part of this problem? At least one problem for sure in your final exam going to ask you isentropic efficiency. Whether it may ask how much please determine isentropic efficiency, or isentropic efficiency is this much. Then what is this value? So either way, you need to know how to determine isentropic efficiency, but we haven't done yet. So let's do it now. To be able to determine isentropic efficiency, you need to know how to convert this turbine into an isentropic turbine. The reason is, if you stick to 8 megapascal, 600 degrees Celsius, 80 meter per second, and 70 kilopascal, 160 degrees Celsius, 140 meter per second, the power output is going to be always 6,000 kilowatt. Then, if you want to have an isentropic efficiency, we expect an isentropic turbine will produce more power than 6,000. That means some of these values may not be true in the isentropic turbine. Make sense? Because you can produce more power than 6,000. Whatever, leaving this turbine should be different. If the properties of the steam leaving this turbine is the same here, then power should be always 6,000. But if you produce more power, there should be less energy left over at the exit. Make sense? So the properties at the exit should be different from this one. Then how different? So we are going to make an isentropic turbine that has one inlet and one exit. And this one produces power, but not 6,000. It will produce much more than 6,000. Then what's going to happen? Does it change the inlet condition? No. At the inlet, it hasn't, entered this isentropic turbine yet. So there's no difference between the actual turbine and the isentropic turbine in terms of the inlet condition. So inlet condition should be the same. 8 megapascal, 600 degrees Celsius, 80 meter per second. Then let's look at the exit. 70 kilopascal is the pressure in the pipe connected to the exit of this turbine. So that pressure should be based on, whatever the pipe, the post, the device. So it depends on, the pressure at the exit does not depend on whatever happens inside. It depends on how this is connected. If that is open to the atmosphere, the pressure is going to be the atmospheric pressure. If it is connected to another pipe, the pressure at the exit depends on the pipe condition. So 70 kilopascal cannot change. So 70 kilopascal. What about velocity? This velocity also depends on, the condition, the where this exit is connected to, depending on the size of the pipe. If it has a narrower pipe, then the velocity goes up. If it has a larger, the cross-sectional area, the velocity will go down. So there's nothing, to do with this isentropic, or actual in terms of this, the velocity. So the velocity should remain constant. So the question is going to be this temperature. Is the temperature still 160 degrees Celsius? Not anymore, because we are going to produce more power, then less thermal energy will be at the exit. So the temperature could be less than that. So one thing is different between the actual turbine and this isentropic turbine is going to be the thermal energy at the exit. And this temperature represents the thermal energy at the exit. Then let's solve this problem. What is the energy balance equation? We already found the energy balance equation, so I'm going to reuse this blue. The energy balance equation is m dot h1 v1 square over 2 is going to be w dot out plus m dot h2 v2 square over 2. Then let's look at this energy balance equation, which value is what we know and which value we do not know. First of all, we know the mass flow rate we just determined. So m dot is going to be 7.17 kilogram per second. What about this H1? At the inlet, we have 8 megapascal, 600 degrees Celsius for the actual turbine. For the isentropic turbine, we also have the same pressure, same temperature. So is there any difference between H1 for the actual turbine and the H1 for the isentropic turbine? No. So H1 should be the same. So H1 is going to be 3,642 kilojoule per kilogram. Now velocity is 80 meter per second. And power, is the power 6,000? Not anymore. So power is unknown. What about this exit velocity, 140? So we have two unknowns. One is the power. The other one is the specific enthalpy at the exit. Can we use the same, the specific enthalpy at the exit? Not anymore, because we have a different temperature now. So the question is, can we determine H2? Let's see. What do we know? We know pressure. Okay, good. Can you determine H2? No. We only know pressure. We need to know another property to determine H2. So what is the other property? Do we know any other property at the exit other than 70 kilopascal? There is one. Isentropic efficiency. Entropy remains constant. Can you determine S1 at the inlet? Yeah, then that S1 is going to be the same as S2. So you know the specific entropy at the exit. So let's find the specific entropy S1. Then we know S1 is superheat vapor, so you can go to superheat vapor table. So there's a superheat vapor table. 8 megapascal, 600 degrees Celsius. Do we know the specific entropy? Yes, this one. 7.0206. This one is the specific entropy at the inlet. So S1 is going to be 7.0206 kilojoule per kilogram Kelvin. Now, since this one is an isentropic turbine, entropy S remains constant between the inlet and the exit. So S2 is going to be 7.0206 kilojoule per kilogram Kelvin. So now we have S2 and pressure P2, which is 70 kilopascal. Now we have two properties. Can you determine H2? Now, yes. Yes, we can. So let's do that. How can we determine H2? We need to know the phase change process first. Oh, wait. We determined it is super vapor at the exit. Can we reuse this phase change process? Not anymore, because we have a different temperature now. So we need to re-evaluate the phase change process at the exit. By how? By using these two properties, the pressure at the exit and the specific entropy that we calculated from the inlet, assuming an isentropic process. So let's make another property diagram, but this time we are going to use this pressure, P2, at 70 kilopascal. What property diagram we are going to make? TH, not anymore. This time we know entropy S. So we are going to make TS diagram. Oh, TS diagram looks new. Is there any difference between TS and TH? Not really. They look very similar. So TS diagram looks like this. How many reference properties do we need? We need T-sat, we need SF and SG. So let's find T-sat, SF, SG. Where can we find these values? From 70 kilopascal. So let me go find 70 kilopascal one more time. This is table A3, pressure table. Let's find 70. Here, 70 kilopascal. T-sat is 89.95. Okay, good. T-sat is 89.95. We need to know SF, SG. SF, here, SG, here. So, the values that we are looking for is, this one is SF, this one is SG. So let me write these two values on this property table. 1.1919, 7.4797. Then we are ready to determine the phase change process at the exit. Okay, so we used this 70 kilopascal to make this TS diagram. Then we are going to use the other property that we know. What is the other property? Specific entropy S, 7.02. So let's find 7.02 on this TS diagram. Where is S? The horizontal axis. 7.02 is greater than SF, less than SG. So where is our system between these two numbers? So what is the phase change process? Number 3, saturated mixture. Between these two, 7.02 is close to SG but less than SG, so somewhere here. So this is our system. So this number is here. So where is our system? This one, phase change process number 3, saturated mixture. We don't have enough space. Use another scratch paper. Okay, then can we determine, now we know it is a saturated mixture. Can we determine H? Not yet. If you have saturated mixture, there's one more thermodynamic property that you need to calculate. What is that? Quality X. The ratio between liquid and vapor in the mixture. So let's find quality X. How do we find quality X? We can use linear interpolation equation, which is SF plus quality X times SG minus SF. Now we know this equation looks very familiar. We did many table problems long time ago, right? So do we know SF? Yes. 1 point, this one, 1919. Do we know SG? Yes. 7.4797. Do we know S? Yes. 7.0206. Then we have everything. Can we determine the quality X? Now, yes, we can determine the quality X. Then what is the quality X? 0.927. 0.927. Once you know the quality X, now can you determine specific enthalpy H? Now, yes, we can use the same equation. H is HF plus quality X times HG minus HF. And here, this X is going to be what? 0.927. So we just need to know HF and HG at what condition? At 70 kilopascal. So let's find HF and HG at 70 kilopascal. At 70 kilopascal, HF is this number, HG is this number. So this is HF, this is HG. So let me write these two values in this equation. 376.7, 2,660, 3,376.7. So we have everything. Can you determine H? Now, yes, you can determine H. What is that H? 2493.3. So that is H at the exit, assuming that we have an isentropic turbine. So this number goes to where? Go back to this energy balance equation, this H. So this number goes up here. I know that you may not like this one, but you know, we don't have much space. So there's a H. Every semester I get a review, and one of the the review saying that that there are too many errors in my solution, but there's nothing I can do. Find me bigger screen than this one. Just too small, isn't it? So H2 is going to be this one, 2493.3. Now we have everything. Can you determine the power? Yes. Now we can determine the power. How much is it? 8,100 88.7 kilowatts, which is much greater than 6,000. So if you have a turbine in this condition, that's the maximum power you can generate, theoretically. The actual power could be less than that because in reality, there are many irreversibilities. But the goal is going to be, if your present turbine has can produce 6,000 kilowatts, then you know that you can go up. It is possible, theoretically. And what is the maximum value? 8,188. Then, how close this turbine to an isentropic turbine? We can calculate that. Isentropic efficiency of the turbine is going to be the maximum value, this one, 8,188.7 kilowatts. But how much power can you produce presently? Only 6,000 kilowatts. So what is the isentropic efficiency? 0.733. In other words, 73.3%. So your present turbine is 73% close to the ideal condition. Then where can we use this information? If you design two different turbines and you want to know which one is better than the others, then how can we do that? Oh, one turbine can produce the 6 megawatt and the other one can produce only 5 megawatt. So you can compare only the output. What about if the inlet condition is different? One turbine, the inlet condition should be, the 8 megapascal and 500 degrees Celsius. The other one is only 6 megapascal and 400 degrees Celsius. So if we have all the, the values are changing, how can we know which one is better than the other? By calculating the isentropic efficiency. So you can calculate isentropic efficiency for any turbine. Then the one has higher isentropic efficiency is better designed because it has less irreversibilities because it has higher isentropic efficiency. Okay? Any question about this problem? 100% sure you will see isentropic efficiency in the final exam. It's not 99%, 100%, 100%. Any question? So basically, you are going to calculate how much power it's going to produce between 6,000. Once you get 6,000, once you get 8,188, then you're good to go. And then, one thing for sure is going to be the inlet conditions should be the same, but the exit conditions should be different because one can produce more power than there will be. As a result, the exit condition should be different, right? So the thing that you are going to, the one property that is not the same between here and there is going to be the temperature. So you are going to neglect the temperature and recalculate based on this condition, isentropic efficiency. What about if it is a compressor? Then you will calculate how much power the compressor is going to consume. And you will do the same here. But again, the exit condition should be different. And what property is different? Temperature. So you are going to neglect the temperature in an isentropic compressor. And instead of this compressor, you are going to use this assumption. Entropy remains constant. That's how you are going to calculate power consumption in a compressor when you have the power values between actual compressor and isentropic compressor. Whichever greater value goes to denominator, less value goes to numerator. That's how you calculate isentropic efficiency. Okay. I think that's all for isentropic efficiency, and we have the last part of this chapter 6, entropy balance. So what is an entropy balance? Entropy balance is an equation similar to energy balance equation, but there is one difference between entropy balance equation and energy balance equation. In energy balance equation, we use, the one principle, which is the conservation of energy principle. So based on that, when we talk about energy, we assume that energy transfer into a system minus energy transfer out of a system should be the same as the change of energy of the system. That is based on conservation of energy principle. However, in terms of entropy, there is no conservation of entropy principle because entropy always increases whenever there is a irreversibility. In real world, always there is a irreversibility. So, can we follow the same equation? No, not anymore. This one is not the same as the change of entropy of a system. Okay, I get that. So, since this one doesn't work, so we give up? No. Then why this equation does not work? Because entropy always increases. Then what about if we take that into account? So entropy always increases. How much? Okay, we can say entropy always increases by this much. Entropy generation. Then why don't we add this term into this equation? Okay, maybe we can do that. Entropy transfer in minus entropy transfer out is not the same as the change of entropy of a system because of this entropy generation. Then let's add this term into this equation. Then this equation sign works. Yes. Oh, we can do that. Okay, so basically we are going to use this form, and the purpose is going to be, that if you use this entropy balance, you can calculate this entropy generation. Okay, that's the end of the story. So we will continue this entropy balance equation, not today, next week after the exam. So let's do a quick review for the exam. So we are going to, the second exam, I'm going to stop the recording.